Hello, everybody. It's a pleasure to have Tobias with us here. He'll be telling us about, I presume, interactive machine learning and thinking about jointly about machine learning and user, and where he's done a lot of interesting work.
Hello, everyone. Thanks for the great introduction. Today I want to talk about how we can improve machine learning beyond the algorithm by not working with the algorithm itself, but also by improving it through working with the user interface, as he mentioned. So in order to better understand what I exactly mean by that, I want to start with an example. Let's say we have this fictitious bookstore, and we want to find out how good the inventory of our bookstore is. So that means we want to find out what is the average rating that people would give to books in our inventory. So the good people we are, we go out and we collect data. And the way we do it is we would show users a book along with a star rater interface and say, rate this book on a scale from 1 to 5, how much you would like to read it. And then, so we do this for n randomly sampled books. And after we collect all the ratings in our second step, we do a very sophisticated inference. Namely, we infer the mean parameter by simply averaging all the values. So we're done, right? No, because we have an angry boss coming in, and she's saying, your estimates are way too noisy. There's too much variance. I don't know what to do with this. So you put your machine learning thinking hat on, and you go back. And you look at this, and you say, well. Maybe this estimator isn't the best. Let's improve this by using some prior knowledge. So kick this out, and let's assume that our ratings come actually from a normal distribution that has a normal prior on the mean. All right, so notice that this is, in principle, an implicit user model because it somehow assumes how the data was generated. And then in the second step, you would just compute the map estimate for your mean parameter. So that should help us reduce the variance in our estimates, but I'm going to argue here that this is not the only way to do this. Actually, if we take a step back and think about what we did here in our little toy problem, in the first part, we actually had people giving us ratings through an interface, whereas in the second part, we had this very sophisticated algorithm to give us the mean rating. But actually, we've only worked really with the second part. And my argument is that we could have equally worked also with the first part. And what we could have done is also swapped out the interface and changed it so that we would show a similar book to the one that users are about to rate, that they've previously rated along with the star ratings they gave. So we had The Hobbit here, and it would show, oh, you gave Lord of the Rings 3 stars. And it is known, people have done that, and you can see in user studies that this reduces also the variance in the rating data that you get. So you've achieved essentially the same or a similar result by working with the interface instead of the algorithm, adjusting the algorithm. Now, what you've just seen is a very crude interactive system. You could even argue it's not interactive, but my point is that even when you move to more complicated interactive systems, such as recommender systems or search engines, the same kind of view should hold. So you have a back-end machine learning algorithm, and you have people that interact with the algorithm through an interface, and both are tightly coupled together through the data. So data that people generate, but also kind of outputted predictions from the ML algorithm. And in this talk, I want to kind of highlight our efforts to work with the two different components here. So in the first part, I want to talk about how we can design better ML algorithms, taking into account biases from the users and from the user interfaces. And in the second part of my talk, I want to start with the people and interfaces side and thinking about how we can design better user interfaces for more effective machine learning by shaping and designing the data that the algorithm then takes as input. All right, so in this first part, I want to start with a paper where we show how to evaluate and train recommender systems using a new approach that relies on causal inference. And as a motivating example, I want to look at movie recommendation. In movie recommendation, we have a population of users, so here, and then a number of movies. And we want to recommend those movies to each user that he or she values the most. In this toy example, we have two user groups, romance lovers and horror lovers. Romance lovers love romance movies, but hate horror movies. And horror lovers love horror movies, but hate the romance movies. And both user groups are indifferent with respect to drama movies. Now, the problem is that in practice, we don't get to observe this full ratings matrix, but we only get to observe a subset. And it is well known that users are more likely to give more ratings for things that they like. So we would see much more 5-star ratings than 1-star ratings in the data. And the fact that these 5-star ratings are overrepresented is due to what is known as selection bias. And this problem is also sometimes called data missing not at random, MNAR. And I already mentioned that there's, this one source of bias that we saw that comes from the users. So the user-induced bias comes from the fact that people are more likely to rate good items or like effects that they would look at more at certain categories more often and so on. But then there's also system-induced bias that comes from advertising making certain items having a more prominent position on the starting page means that users are more likely to click on it and rate it. The obvious question is, what happens if we just ignore selection bias and apply our standard machinery here? Notice that this is the kind of most frequent approach in the literature, modulo a handful of generative approaches that we'll compare against later. So what happens now? When we ignore selection bias, it turns out that we can be horribly misinformed. Suppose we want to deploy a new recommender policy, here, Y hat. And Y hat actually turns out to be pretty crummy, so it recommends mostly 1-star movies to users. I've indicated that here as the boxes. And what happens now if we evaluate it on previously collected data is the following. Suddenly, our crummy policy looks pretty good because the overlap with the 5-star ratings is pretty significant. So we would be misled and arrive at the wrong conclusion because of selection bias. So that's not good. And a very similar thing happens also when evaluated predicting ratings. So you complete the matrix, like in the Netflix challenge, instead of policy evaluation. And we have two systems that we are evaluating. So the first system ignores the two groups and just predicts all 5s. So that I've indicated, and makes a large error on the full ratings matrix. So you would have a lot of errors here. I've indicated that in deep red. Now, the second policy is better because it recognizes that there's this diagonal structure. However, it makes a small mistake, a small error on the drama movies by predicting 5s. And I've indicated that in light red. What happens now if we evaluate these systems again on observed data? Well, for the first system, we make 5 errors, since there's not a lot of 5-star, since there's not a lot of 1-star ratings. And then for the second system, we make far more errors because there's just more of the 3-star ratings in the log data. So this actually makes the second system's performance look much worse, and we would prefer the first system here. And again, we came to the wrong conclusion and picked the bad system because we were ignoring selection bias. So that should hopefully, yes?
Also, 5 is not as much different than 3 as 5 is different than 1. So.
Yeah, but I mean, in this example, if you kind of try to sum it up, then you would still see that this would outweigh, the number would just outweigh the difference here. But that's a valid point, yeah. So the key idea in our paper is to kind of solve this by connecting it to the potential outcomes framework from causal inference. And in the potential outcomes framework, you often think about patients getting treatments, for each patient, you would only get to observe the outcome of the treatment which he or she got assigned to. And the counterfactual question is then how a patient would have fared under a different treatment, different than the one that you prescribed. And you can think in a similar way about movie recommendation, at least in the policy setting, where now users get prescribed movies, and you want to find out how users would have enjoyed movies different from the ones that they've potentially watched. And in order to do that, what it turns out is that we need to understand mainly how people were assigned movies or treatments. And this is also called the assignment mechanism. To make this more precise, in recommendation, this actually boils down to knowing what the marginal propensity is, marginal probability is for a rating in our ratings matrix to be observed. And this is also sometimes called the propensity. And then we can use the inverse propensity estimator, which is well known, and I mean, I think most of you are very familiar with it. Has been used in many other settings, domain adaptation, as well as reinforcement learning. And the idea is, or the way it works here is, so you would sum over all individual losses and then reweight each individual loss by the inverse propensity. And that gives you an unbiased estimate of the loss. And this also extends to other performance measures that you can write as a sum of individual losses. And on the right, you can see the propensity matrix that I used to generate the example, the observed pattern you saw earlier. So we had a high probability here, a smaller one here. And if we just had used these propensities along with the IPS estimator back then, the problems that I mentioned earlier coming from selection bias would have gone away. So really all we need is this propensity matrix here. Now, how do we get this? Well, there's actually two settings. In the first settings, the experimental one, we know the propensities because they were under our control. So we had an ad placement system. We had something that stochastically put things in front of users, and we just record these probabilities. The second setting is a little bit more intricate. In the observational settings, users self-select. And in that case, we need to estimate these propensities. And that corresponds to inferring the parameter of Bernoulli random variables, namely the ones in the observation matrix. Notice that this observation matrix is fully observed, so it contains a 1 whenever rating was observed and 0 otherwise. And to do this estimation, we can include side information such as the user user item features, X if available. And since this is a standard supervised learning task, we can use a variety of models such as logistic regression, naive Bayes, or Bernoulli matrix factorization, etc. So now that we talked about how to fix evaluation, we can apply the same ideas to learning. And our idea was simply to couple together ERM, empirical risk minimization, with the inverse propensity scoring estimator. So now we would pick the hypothesis, the model that performs best under the IPS estimator. instead of the naive one that just has an unweighted loss. To make this more concrete, the objective below is probably all known to you. This is a standard mean squared error loss matrix factorization with regularization terms. And we know how to solve this and scale this. And the only thing that changes now when you use the IPS estimator is that you get this propensity weight here. So really not that much, but I think conceptually that this is a bigger step. So just to make this framework a little bit more clear, it's very modular in that first you kind of estimate and pick and estimate a propensity model, and then in the second step you would use your ERM objective together with the estimated propensities. And this is different from a generative approach where you often kind of reason about how the data is missing, and then you have a model that explains how all the data comes about. And those two are coupled together via latent variables, and that makes it a little bit more sophisticated, but we'll also compare against them later. So before I get to the empirical results, I want to quickly talk about some theoretical insights that we provided in the paper. It turns out that there's this additional trade-off between bias and variance that comes from the propensity estimation. So if you bound the true error with the empirical error, you get a very familiar looking bound, except for the colored terms here. So what you get is this bias that is a penalty that tells you how far you are off from, like, the estimated propensities are off from the true propensities. And then there's also this variance component that is due to the estimated propensities. So just to instantiate this in a naive method would be high in bias, because that is kind of mismatched, but low in variance because those are constant. But yeah, our method would be like for perfectly estimated ones, we would have no bias, but higher variance usually. And this also kind of shows that it might be beneficial in some scenarios to trade off some bias, some lower variance at the cost of a small bias by overestimating the propensities. Okay, so to evaluate whether our method improves performance, we did an empirical study on 2 real-world data sets. The first data set was one that we collected ourselves. People went shopping for coats and also rated them. And then the second one is from Yahoo, where people listened to songs and rated them. And both data sets were special in that they contained a missing completely at random test data set, where people were actually more or less forced to rate a randomly subsampled set of items, different from the ones that they were browsing earlier and rating themselves. And so what we did is we trained on the missing not at random training data and then evaluated on the missing completely at random test data. And we compare against the latest generative approach that we could find from 2014. And on both data sets, the propensities were estimated via logistic regression using user item features in the code data set and using naive Bayes for the song rating data set. So, and then for the so the results show that our method outperforms both kind of the naive matrix factorization as well as the more sophisticated generative model on both losses and on both data sets. So encouraging. And so by the end of this kind of part, I hope that I was able to convince you that this discriminative propensity scoring idea is a nice one because it's modular. It directly optimizes the target loss and not just some log likelihood. There's no latent variables, and it's usually scalable in the same way that the original problem was scalable in. Yes?
So assuming both these data sets did not have known propensity scores?
Non-propensity?
Known. So the actual presentation was not done using randomization that you
Yeah, so both were in both data sets were using the observational setting.
Okay.
Yeah.
I was just curious if you did any experiments where you tested, like how close can you come to the Oracle probabilities? Like if you actually had a randomized experiment.
We have some we have some synthetic experiments where I can show these later. I think they're at the end. But so we had some synthetic experiments where we tested how robust this kind of because we actually just care about the final ERM step, how robust they are to the estimated propensities as well. And it turns out they're quite robust. Okay. So for the remainder of this part, I want to talk about a follow-up project where we apply very similar ideas to debiased learning to rank. Just to get everyone back into the learning to rank setting, we work with the query xi usually. Let's say it's winter shoes, and then we have a ranking algorithm in production, S-bar, and that outputs a ranking. And then we collect click logs from that ranking algorithm. So people click on B and D, and we would store that. And then our task is to take all this data, have a learning algorithm that hopefully outputs a better ranker. The traditional way of doing learning to rank is to hire judges that annotate each result. So you would hire people, and they would go through this ranking for the query shoes, and then would say, well, result C is relevant, F and G is relevant. So when you want to evaluate, this is also called full information learning to rank. And it's straightforward to evaluate a new ranker because on the same query, because you just reorganize the results, and then you can compute the loss function here. Everything is known. However, it's often more convenient and also cheaper to work with implicit feedback from click logs. And to be still able to learn, what you do is you assume a certain user model. In the weakest case, that a click indicates relevance. So here, user clicked on result C means that we assume this result to be relevant. The other ones have question marks. And the problem is, however, that we only have partial information. And so when we want to evaluate a new ranker, we can't compute our loss function directly because there's missing data, and it is missing not at random. And was that a question?
Yeah. Should you assume A and B are not relevant?
Yeah, or at least not. Well, that is something you could do, that some click models do. But in even the simpler case, you could just say, I assume only that a click means relevant. That's kind of the click model I'm assuming. That's one of the most simple ones. Yeah. Okay. So if we want to evaluate a new ranker, we can't compute the loss function here because there's so many question marks. And it turns out, however, that we can compute it in expectation in a similar way as before. So just to introduce a little bit of formal notation, we're working with a loss function delta here. Given the relevance labels, binary relevance labels, it tells you how good a ranking is. And in our paper, we use the sum of ranks of the relevant documents. So if this was the ranking being presented, then you would add up rank 3, rank 6, and 7. That would give you a loss of 16. Our user model was, again, the very simple assumption of a click means relevant, but that kind of poses the question, what does no click mean? Well, we could either make the assumptions that you made, but in general, we could reason about, well, either a user did not observe a result or the result is not relevant. It turns out that we don't need to think about this so much because it's all solved by just, again, knowing the assignment and observation mechanism. And again, we need to estimate propensities that indicate how likely it is for a relevance label to be observed. So here, we would say that the probability of observing this relevance label here is 0.5. And then again, we can use the IPS estimator to evaluate, to compute the loss of a new ranking, but we only sum over the clicked results here because of our user model, because of the assumption. That's where the assumption comes in. Yes?
Do you assume that this probability depends or is independent of the location where you show that?
This you can plug in different kind of propensity models here. What we did is that it is dependent only on the rank. So a position bias model.
It's like there's only position bias.
Yeah, in this, but you could think about other biases. Yeah, but we only, I mean, that is the main part.
And in your data, there is only one click per data.
No, it's multiple clicks per query.
I see.
Yeah, and then
You're
to
assuming that relevances are binary now?
yeah, that's also why it simplifies to kind of that setting. And then to get the unbiased risk estimate for the entire data set for the entire ranker, you would just go and average over all queries in your log. And so we coded this up and as an SVM rank. So this is a propensity weighted SVM rank, which optimizes the loss you saw earlier on the previous slide. And we compared it against a standard SVM rank, which didn't use any weights, and a hand-tuned production algorithm that was in place. And we tested it on an academic search engine, archive.org, probably all know it. We estimated the propensities via a small intervention experiment where we swapped pairs of results and then evaluated whether our propensity-weighted SVM rank is better by interleaving the results of it with another method and then counting how many clicks each method got. And what you can see here is that our propensity-weighted SVM rank significantly wins against both the production and the naive method by just taking, and that one is just taking into account position bias. So yeah, that kind of concludes my first part, but I also want to briefly mention a bunch of observations. Did you have a question?
Yeah, if you just assumed people saw everything above what they clicked and nothing below.
No, we didn't even do that. We had a really Bernoulli, like each position was like a coin flip, and that was kind of the propensity.
Yeah, but I'm curious how strong of a baseline is that compared to the position-dependent thing?
How strong of a baseline that is to position-dependent thing?
It is position-dependent because the coin is different at each position.
Yeah, exactly. Yeah.
But Jake was asking about as a baseline.
As a baseline, you just could have filled in missing data as Dave was suggesting and just assumed everything above was a true zero.
So I think we talk in that paper also about, you can use more sophisticated click models. There's all kinds of, generative processes that you can put into, you can make it more sophisticated how you estimate these propensities. But I think this really just is, it's general enough to incorporate these more sophisticated propensity models. We just wanted to show that even by doing the simple adjustment, you can do much better than. Less sophisticated?
Yeah, so you're suggesting don't use propensities at all and just treat everything above as a zero.
Oh,
In strain your ranker on that data.
Your last click.
Yeah, okay. That's more like the kind of the pairwise preferences one, which is I don't know why I think there were some experiments. I need to look that up again. But yeah, that's a good point. Thanks.
I'm also curious, in archive data, do you actually see multiple clicks? I don't know, like my own use of archive search is very much like I'm looking for a very specific paper, I find it, I read it, and I don't know if others use it in a different manner, but I'm curious.
This is, yeah. This is the full text search, though. This is different from the just where you want to find the specific one. Notice that there's this full text search drop box, and then you land on the full text search. And there's this one is usually more fuzzy. Like the full text search is not as precise. So you would specify keywords, and then you would get back a ranking, and not so much matching like in a Boolean way. So yeah, I mean you would see people click multiple times because. Yeah, to find something they were interested in, just in general exploring. All right. So I want to move on to the second part, where as an intermediate goal, I want to talk about how we can aim to design interfaces that allow us to obtain more and better feedback data, all while not hurting user satisfaction. And that is because better data will then allow us to improve our predictions. So really, I want to focus on this outline connection here, like users and interfaces like affecting the data that the machine learner gets. In this first, so how can we get better and more feedback data? In this first project that I want to talk about, we came up with a new interface that allowed us to collect a new type of feedback signal. So I know it's lunchtime soon, so I want to run a little experiment with you. So I want you to stare at this for 10, 15 seconds, figure out what you want to have for lunch. All right. Who knows already what he or she wants for lunch? Ooh, wow, we have some, yeah, okay. Well, not too many, but some decisive people, I like it. But in general, making a decision is hard here. Why is that? Well, there's a large set of options. You are probably not familiar with all the inventory, like what are the options out there. And you're also often uncertain about your own preferences. Did you have pizza yesterday? Like, are you going to go out for Chinese tomorrow? So it takes a lot of thinking. And our starting point here was really to think about how we could support users to drive feedback generation. And obviously, in the long term, we want to have, provide better recommendations. But for that, we need the improved feedback first. But in the short term, we can think about how to reduce cognitive burden. And I'll come back to that in a second. So what you've just seen, this example of picking something to eat is an instance of what we call session-based decision-making, where your goal is to choose one option, and the information need is fixed. So you wouldn't just do something else. Examples for that are picking a movie for tonight, searching for a recipe, comparing laptops online, planning a trip, booking a hotel, and so on. It turns out that a common strategy employed by people in this session-based decision-making is called consideration set formation. And basically, it works in two steps. In the first step, you would narrow a large set of options down to a smaller set called the consideration set. And then, so I would go through and I would look at, that looks good. The quiche looks also good. And then based on that consideration set, you would then make a decision. And so I would now reason and think, well, I had pizza yesterday for dinner. How about the quiche? So decision done. So this kind of strategy or this kind of insight was the main inspiration for our interface. The session-based decision-making we studied was obviously not on food choices, but on movie choices. So below is an interface that resembles that of many online streaming providers. So you can scroll, you can kind of filter and get more information by clicking on it. And our idea was to augment that interface with what we call a shortlist component. So users could click on a plus button or drag and drop items up there to keep track of them. So this was kind of a list of items that they're currently considering or interested in. And to find out whether or how that shapes kind of the feedback data that we want. We ran a user study where we compared the interface with a shortlist component against the one without one. And the task prompt that we gave people in Amazon Turk was, imagine a very good friend of yours is coming to your place to visit. After hanging out for a while, you plan to watch a nice movie together. In this experiment, you'll be asked to select a movie to watch with your friend. And so we had 60 people come in, most of them PhD students. 3/4 were male, 1/4 female. And we randomly assigned them to one of 2 flights. In the first flight, they started with the shortlist first. And in the second flight, it was last. And in each flight, they had to choose a movie 8 times. So each of these corresponds a new session. And each session, they had a fresh set of movies, of 1,000 movies to pick from. And then we collected the feedback data and also user feedback through surveys. So now we can look at, do shortlists lead to more data? That was kind of our goal, and can we drive users somehow to give us more data? And if you look at the movies with interactions, like that is the unique number of movies, then without the shortlist, people click on 2.7 items on average, 2.8. But with a shortlist, it's more than twice the amount of movies. So you get 5.7 kind of positive interactions in each session on average.
By positive interaction, you mean like click on the details and
clicked on the details or shortlisted. And notice that something that was shortlisted didn't necessarily have to be clicked on, because it might have been a known movie, and then in that case, you don't want to look up more information, but you would still shortlist it because you want to keep track of it. You're like, oh, that's a classic.
how is that 1,000 movies like sorted? Like, what is the order when it's displayed to the user?
It was recent movies first, and then by the number of stars. So by year, and then within each year, number of stars.
Number of stars is the public.
IMDb score.
I see. Okay.
Yes, back there.
2 questions. First is, in your interface, do you categorize all the movies into different genres? Like I can.
Yeah, you can.
I have to browse 1,000.
Yeah, you can browse by selecting the genre here.
And second is, how is this different from something that Amazon is doing? Like I can add some movie to my watch later or my favorite list. I don't mind not watching right now. I just add into that section.
That's a good question. So shortlists are different in that they are only kind of temporary and really tied to the session. It's not something that you add to your, like, I want to watch later. It's not persistent. This is really just for the decision making, for the single task, and not so much. I mean, people hack this in all kinds of ways. They open tabs. I add stuff to the shopping cart just to remember it, even though I don't want to buy it. It is different. That's hopefully, yeah. Okay. So we have more than twice the amount of training data, but does that also help recommendation? And that's what we looked at next. Oh, sorry.
Maybe I missed this. How's the shortlist constructed?
The shortlist is something users actually come up with. So they add something that they're interested in during a session to it. It's empty when they start, and then it's just like a stack of books when you go to a store that you are considering.
Without the shortlist, they don't have the ability to make a shortlist. Is that what you mean?
Sorry?
What's the without shortlist condition?
Without, they don't have that ability. They have to remember it themselves, or write it down, or do something else. Yes.
But in other product categories, people can put it in the shopping basket without purchasing in the end, right? Just put in my shopping basket, and then the time when I check out, I decide which one I want to buy for sure.
Right. Yeah. That's what we called kind of a hacked way of shortlisting, and that was also the inspiration to make this kind of an explicit interface component rather than, I mean, sure, you can find ways around it, but our idea was really to study how this influences when we give it to people explicitly.
Then in addition to the movie category, do you think how could this be used for other domains or in practice?
Oh, I think having the ability to shortlist stuff and remember things you're currently considering, I think that goes for many applies to many of these one choice tasks where you want to figure and compare things. Like choose one thing among n, and then whenever you can support that, I think shortlists are a good interface component. Whether or not it should have this form as a visual, component, or something else, maybe a smaller or like on the side. That's, I think, up to the interface designer. But I think it is important to reason about how easy it is to add things to it, and that it really supports users in their tasks. You don't want to put a too high cost, because adding something to the shopping basket hides it again, and then you need to make an extra navigational effort to go to the shopping basket. So these are all things to consider. Yes?
So in the 5.71 that you have more data, you're counting a 1 every time a person is adding to the shortlist?
Yes, but I would count the unique items. So if something was clicked on and shortlisted, it would only count as 1.
Okay.
Yeah. So it's not just.
So like out of so the fair comparison is how many clicks you have out of the session, basically, right? Between the one with shortlist and one without.
Why would that be?
Because you're counting more clicks. If I'm just adding things to shortlist,
yeah,
not clicking anything,
yes,
it would be in the other case, it would be the same of 0 clicks.
Yes.
Without shortlist.
Yeah.
But you're counting now the shortlist.
I'm counting with
571.
Yeah, I'm counting with the shortlist, because that was the whole goal, to kind of collect a new type of feedback data.
So that's even if a person doesn't watch anything, you will still have more data.
Yeah.
If it's a little bit less.
I mean, in this case, they were forced in the end to choose a movie to terminate the session. So in the end, they had to choose something, whether they use a shortlist or whether not. Yes?
I think if I understood the last question, there's a little bit of an apples to oranges comparison here, right? Where like I could just drag a movie into the shortlist, or I could click on it, look at it, and then move it into the shortlist. And if I didn't have the shortlist, and the equivalent of the first thing, do you understand the difference? So if I just move a movie into the shortlist without looking at it, just imagine I have like 2 levels of interest, right? One is like, oh, I don't immediately want to reject that movie, and another is like, oh, I'm actually like seriously considering that. And I might put both in the shortlist, but if there's no shortlist category, then you're only going to see the second type of click.
Yeah, exactly. That's the point of the shortlist, I think, to elicit that type of feedback.
But it's not clear that it's doing anything, right? You could just be buffering the.
Yeah.
Yeah. I think his next slide will so I think that the point is to give more data to the algorithm so it can do better in future. And if you're doing stuff in your head, maybe you accomplish your task one off.
Yeah.
There is less training data for the algorithm.
Yeah.
So
Okay, but you're not interpreting the different number of clicks as meaningful in its own.
Not yet.
No, not yet.
Okay.
Not yet. That hopefully answers a bunch of the questions. And I'll also talk more about how users feel about the shortlist. So in the prediction task, we kind of took the movie from each session and held it out that people finally chose. And our goal was to rank it to the top of, in a set of random movies. And the training data were all displayed movies in the session. We used the ranking SVM, and as feedback, we said that items that were examined, clicked on, or if available, shortlisted, should be ranked above skipped items. We didn't discriminate between the 2 types of feedback signal. And then in the test data, we embedded the chosen movie in 99 random movies. And we measured the mean reciprocal rank, which is 1 over the position where that movie occurred. So 1 over 100 would be worst, and 1 is the best. So if you consider the MRR of a random baseline, and you learn from the sessions that had no shortlist, you get a small improvement. Well, that's not so great, you think. But once you learn from sessions that had the shortlist, so use that kind of feedback data, the new type of feedback signal that you collected, you actually are able to increase your MMR quite significantly. So why are people willing to put up with this? Why are they even using the shortlist? In order to understand this better, I want to break it down into 3 smaller questions. So first, do users appreciate the shortlist interface? Second, do shortlists increase choice satisfaction? And third, how do users adapt their strategies? And yes, users really prefer the shortlists. We asked them to state a preference between the 2 interfaces they interacted with, and most of them either strongly or prefer the shortlist over the no shortlist interface. Moreover, people used them in over 93% of all sessions, even though they could have just skipped the shortlist. Are people more satisfied with their choices? Is another question we looked at. So we asked them, which interface do you think gave you more satisfaction in terms of your final choice? And again, most people strongly prefer the shortlist interface. So that's another positive benefit of shortlists. And then lastly, how did users adapt their strategies? This was more to understand how adding a new interface component also changes the way people behave. And so what we did is we asked to self-report the strategies that they used. And so first, good, which was the most frequent one when they didn't have a shortlist, was they picked the first good item, which is called satisficing sometimes in psychology. Track multiple is the consideration set strategy. Track 1 is just one best option currently, and then choosing that in the end, and other is something else. Now, when you give them the shortlist, then most people switch to this strategy, to the optimizing one. So with shortlist, they satisfy really less and they optimize more. So you can really influence also by the interface how people interact. And moreover, in their statements, people reported that they had lower cognitive loads. It was easier to keep track of things with shortlists. So shortlists really I hope that I was able to motivate that shortlists not only helped long term because we were able to provide improved recommendations, but also short term we had reduced the cognitive burden on users, and we were able to increase user satisfaction. Is that a question?
So shortlist people are very familiar with, right? So there's a habit there that goes into it because a lot of people are familiar with shortlist. But did you test this with a completely new UI mechanism, not shortlist, something very different?
That's a very good question, and we haven't, but I'm sure there is many other ways to support users. I mean, this consideration set formation is just one theory of how people, or one strategy that people employ when it comes to making decisions. But there's other strategies as well, and I think a good UI should make it possible to support a multitude of these strategies really. So thinking about along these lines is very interesting. Yeah.
Did people take longer to make their choice without a shortlist or with a shortlist?
Did people? I think yes. We found a slight increase in session length. Yes. Yeah. Yeah, because they could be good or bad depending on what you're optimizing for as a systems designer. But we looked also at perceived satisfaction. Were they happier with what they did? Because giving up, might not make you happier, even though you're more effective.
So you may have talked about this in your algorithm for the signals.
Yeah.
The movie in the shortlist, the movie people may click on, but they didn't put on the shortlist. Those signals, do you put the different ways in training the algorithm? Do you find the ways influence the performance of the algorithm?
We didn't use weights, but what we did is we said that we had another.
The shortlist could be 2, and the most click now in shortlist could be 1.
Yeah.
There's different ways to play to see maybe
right.
Way to
What we did in the paper is that we we ran also an experiment where we said that shortlisted items should be ranked above just clicked items that were not shortlisted. So shortlisted and clicked is stronger as just clicked, and then that is stronger than any the skipped items, but that didn't improve performance.
Another note I found, I think is maybe something interesting you can experiment is the number of the spots available in the shortlist. Because maybe without shortlist, people just think just pick a random one. But having this box above, people have a mindset, maybe I need to fill all of them. And the longer the list is, I'm going to explore more to see whether that can influence. You'll give some go.
Yeah.
Subtly, people just fill in the go.
Yeah, like the big bowls when you go and get frozen yogurt, and you're like, oh, this is nothing, and you pay $15 for it. Yeah, that's a good idea. It's really cool. Okay, so just to move a little bit further, I want to quickly talk about other ways of collecting more and better feedback data. And one way was to come up with a new interface. But another avenue is to keep the existing interface and just work with the incentives, changing certain things. And that's what I explored in these in the following two projects. So here we kind of looked at how we can shape the feedback data we get using inspired by information foraging theory, which explains how people seek information in unknown environments. And I'm not going to go into too much detail about it, but practically what that meant is that we examined how two things influence users' feedback, implicit feedback. First was information access cost, which we mapped to whether you could click on an item for more information or hover. So hovering obviously is lower effort because information just pops up. Clicking required you to open a pop-up, then close the pop-up, so higher cost. And then information sent was the second axis, where we varied the length of the information description. So in the weak sent condition, there was nothing shown below the posters, just the posters. And in the strong sent condition, you had the number of stars, the title, and the genres along with the year. What? Sent? Because it's inspired by how predators were hunting for prey. So information, yeah, that's information foraging theory comes really from the carnivores, and they smell something and then they follow a lead, and if the scent is strong enough, they follow a cue. So that's really how this was inspired. And I don't know, it's just the vocabulary they use. So what he found is by exploring these interventions is that feedback quality, as we mentioned it, as we measured it in the paper, was not affected, but feedback quantity is something that that we were able to shape, and we were able to increase it significantly by lowering the information access costs. So hovering really made people more likely to provide feedback, and we were able to increase it moderately by weakening sent, by showing them less information, so they had to click. This is also what you would expect. But this is another kind of knob that allows you to tweak the feedback that you get. However, notice that here, people in the user survey that we asked, people prefer the strong sent. That is because it shows more information up front. But from an ML perspective, you might sometimes prefer showing less information, so people would also give you the feedback you want, even though they're just mildly interested in. So the optimal ML and HCI design points do not have to coincide, even though for the shortlist that was the case. In general, it doesn't have to be that way. And then this is the final project really that I want to talk about. This is this year's Wisdom paper, where we looked at the cost of expiration from the user's perspective. Our goal was to kind of collect feedback data, look at how we can collect feedback data from expiration while maintaining user satisfaction. Just to familiarize, I mean, most of you are very familiar with this, but let's quickly talk about the exploitation and expiration trade-off. Let's say you have a user that likes Finding Nemo. Based on that information, you could exploit that fully and recommend movies that are very similar in order to maximize short-term user satisfaction, or you could try to explore and cover all possible users' interests, so you learn more about the user in the long run and make you know, a diverse set of recommendations here. But I mean, there's obviously this trade-off, and we studied this trade-off from a user perspective. And so what we did is we created what's mix-in expiration, where we mixed in items from the expiration policy into items from the exploitation policy, which was just a content-based recommender. And then we looked at how people behaved, as well as their satisfaction and the feedback signal. So what we found is that good news, limited expiration is cheap, meaning that if the amount of expiration is not too large, impact on user satisfaction and the feedback and quantity is minimal, not significant. But once you move beyond a certain point, then you get this nonlinear increase in cost. So if you still you know, you use some slots for expiration, that's fine. You go, you know, past a certain point, you really hurt users.
Is this bigger like a cartoon illustration?
This is a cartoon. This is a cartoon illustration, I should say at this point, if it wasn't clear, because it says good and bad, and I don't know. I haven't found it. Yeah, I want to, you know, this is just a sketch of, but for more details, I'm happy to talk to you. But this is essentially what we found. So I think this is also a step towards better understanding how we can gather data. Yes?
But it's not clear that, you know, you have to do, like, the learning performance may not be monotone in the amount of exploration. If you only explore, your algorithm might still suffer. At some point, you start to exploit. So it's the sweet spot of, you know, not, you know, hurting the user is the same as, you know, good enough in exploration for learning.
But isn't user satisfaction kind of like the objective that you want to exploit for?
But not for long. Well, I want to maximize long term.
Yeah, I'd rather say that this is kind of gives you an upper bound on how much you at any given point you should explore, and then you can obviously, the more you kind of stay on the exploitation side, the better it will be once you've acquired enough information. Okay. All right, so yeah, that brings us close to the end. I just want to quickly touch upon some other work that I've done, mainly on how to evaluate systems better. So I've worked on evaluation of ranking functions, of word embeddings, and then how to combine data from multiple logging policies to evaluate a new policy. And most importantly, I want to thank my great collaborators, all the Cornell professors I worked with, my MSR mentors, and all the great Cornell students, both undergraduate and graduate, that I had a chance to work with. And moving forward, I just want to give you a brief outlook on what my vision is. My vision is really to have a highly accurate and useful interactive systems through a holistic design. And as I've argued, that requires us to think about how components of an interactive system work together. And I've already laid out some examples of how to do this, but there's plenty of other exciting questions left. Like on the algorithmic side, you can think about how to learn or how to design online experiments so that you kind of can learn optimally from log data, take care of the biases there. You can think about including other components, which is growing area, fairness, transparency, interpretability, and so on. And then from the user standpoint, I like thinking about putting users in control of their predictions, because the shortlists give them a way of express what they're interested in, but you could think even further, what are good mechanisms for users to specify what they're interested in, or to, you know, give feedback to a system in a more explicit way that also maybe benefits them in the short term. And yeah, in general, I think I've only explored a bunch of incentives for data generation, but there should be a whole zoo of possible patterns and mechanisms out there. And yeah, to wrap everything up, I hope I was able to show that there's really multiple complementary pathways to improving machine learning beyond the algorithm. In the first part, I talked about how to prove ML in interactive systems by understanding the biases in the data, and then we used counterfactual techniques from counterfactual inference that allowed us to include these biases into learning to build more robust ML systems. And then the second part, we started by thinking about how people work and how they interact. And that allowed us to design and shape, design interfaces so that we can shape and maybe collect new feedback signals. So yeah, that I think concludes my talk. Thanks.